Welcome back, everyone. Ready for another deep dive?
Always.
Today, we're shining a light, literally, on the fascinating world of luminescence.
Ooh, luminescence. Sounds intriguing.
It is. We'll be focusing on a study from the Journal of Luminescence.
Okay.
It delves into two compounds, terbium oxalate and europium oxalate. They're like tiny spotlights at the molecular level.
Wow. Tiny spotlights. So what's the big deal about these compounds? Why are scientists so excited about them?
Well, they hold the key to understanding some pretty fundamental principles of how we can actually control light itself.
Control light itself. That sounds amazing, but how is that even possible?
It all comes down to their unique structure and the way they interact with energy. But before we get into the nitty-gritty of that, let's start with the basics.
All right, back to basics.
What exactly are terbium and europium oxalates? What are we dealing with here?
So they're chemical compounds, right? Formed when you combine rare earth elements, specifically terbium and europium, with oxalic acid.
Rare earth elements? I've heard of those, but I don't really know what they are.
Yeah, so these elements are called lanthanides, and they have this really cool property. They emit light when they're energized.
Like they glow.
Exactly. It's kind of like tiny rechargeable batteries of light.
I like that analogy. So in this study, how did they get their hands on these terbium and europium oxalates?
They grew them as single crystals. Imagine like small faceted gemstones.
So we're talking about tiny glowing gemstones. This is getting more and more interesting. Okay, so we've got these tiny gemstones that can glow. But how do they produce such vibrant colors? What's the science behind that?
Right, so it's all about a process called Ligand-to-Metal Energy Transfer, or LMET for short.
LMAT kitschy. But what does that actually mean in the simple terms?
Well, imagine a relay race. The oxalate ligand is the first runner.
Okay, I'm following.
It grabs the energy baton from UV light, right? Then it passes that energy to the terbium or europium ion, which sprints across the finish line, releasing that energy as visible light, those vibrant colors we see.
Wow, that's a fantastic analogy. I can almost see these molecules racing around, passing energy back and forth. So the oxalate acts like a middleman, capturing the energy and then giving it to the lanthanide to put on the light show.
Precisely. It's a beautiful dance of energy at the molecular level.
This is fascinating. Now, the researchers use different types of UV light, right? Shortwave and longwave?
Yes, exactly. And what they discovered about terbium and europium is where things get really interesting.
Oh, I'm definitely intrigued. What did they find?
So they noticed that terbium oxalate, which glows bright green, had a quantum yield of 61.3%.
Quantum yield, remind me what that means again?
It's essentially a measure of how efficiently a material converts absorbed energy into light. A higher number means a brighter glow.
Okay, so terbium oxalate is pretty efficient at converting energy into light, hence the bright green. What about europium oxalate?
Europium oxalate emits a beautiful red color. However, its quantum yield is lower, about 39.8%.
So terbium's the star athlete here, winning the energy transfer race and putting on a brighter show. But why is terbium so much better at this energy transfer thing?
Well, it's not just about raw talent, it's also about technique. In this case, structure.
So it's like having the right form for that final sprint in the relay race.
Exactly. The researchers used X-ray diffraction and Fourier transform infrared spectroscopy.
Big words.
Yeah, fancy techniques to study the crystal structure.
Okay.
They found that the specific arrangement of atoms within terbium oxalate's crystal structure makes it exceptionally good at receiving that energy from the oxalate and then releasing it as light.
So the arrangement of those atoms is like a perfectly choreographed routine for maximum glow. It's like everything's in the right place for that energy to flow smoothly.
Precisely. The structure dictates how smoothly the energy transfer happens. It's amazing how such tiny differences in structure can have such a big impact on the intensity of the glow.
It really is. And speaking of tiny differences, didn't the researchers also look at how water molecules, those little guys, affect this whole process?
Yes. They wanted to see if the water of crystallization, the water molecules trapped within the crystal structure, could influence the energy transfer.
Interesting. I wouldn't have thought about water playing a role in all of this.
Right. It's kind of counterintuitive. They compared two forms of terbium oxalate.
Okay.
One with 7 water molecules, called the heptahydrate, and one with 10, the decahydrate.
So one's a bit more hydrated than the other. What did they find? Did the extra water make a difference?
Surprisingly, the terbium oxalate heptahydrate with fewer water molecules actually exhibited a much stronger charge transfer band.
Hold on. A stronger charge transfer band. Remind me what that means again.
It basically means it's much better at absorbing energy from the UV light and then passing it on to the terbium ion.
So it's like having fewer obstacles on the track for that energy relay race. But why would fewer water molecules lead to better energy transfer? I would have thought more water would mean more energy to pass around.
It seems counterintuitive, but those water molecules can actually get in the way.
Really? How so?
Think about it. Water molecules have a positive and negative end.
Right, like tiny magnets.
Exactly. And sometimes these little magnets can disrupt the perfect arrangement of atoms within the crystal, making it harder for the energy to flow smoothly from the oxalate to the terbium.
Ah, I get it. So fewer water molecules, less interference, smoother energy transfer. It's like clearing the track for that final sprint to produce a brighter glow.
Exactly. And this seemingly small detail about water molecules actually has big implications.
Oh, how so?
By understanding these interactions, scientists can potentially fine-tune the structure of these materials to create even more efficient light emitters.
So we're not just learning why these crystals glow. We're learning how to potentially control and enhance that glow for, like, real-world applications.
Absolutely. And that's where things get really exciting, because this research has the potential to revolutionize the way we think about lighting technology.
Okay, now I'm really on the edge of my seat. Let's talk about those real-world applications. But first, a quick break. We'll be right back to illuminate the future of lighting technology. Don't go anywhere. All right, so we've explored the chemistry behind these glowing crystals and how those tiny water molecules can play a big role. But you hinted at something really exciting. Real-world applications for all of this. I'm dying to hear more about that.
Well, think about how much we rely on artificial light, right? From homes and offices to street lights, even our phones and TVs, it's everywhere.
It really is. I never really thought about it that much before.
And right now, there's a huge shift happening in the lighting industry. A revolution, you could say.
You're talking about LEDs, right? I know they're way more energy efficient than those old incandescent bulbs.
Exactly. LEDs, or light-emitting diodes, are quickly becoming the standard. But there's a specific type of LED that's super relevant here. WLEDs. That stands for white light-emitting diodes.
White LEDs, that's interesting. I always thought LEDs could only produce specific colors, like red or green, not white.
That's a common misconception. There are a couple of ways to create white light from LEDs. One common method uses a blue LED paired with a yellow phosphor. The blue light excites the phosphor, causing it to emit yellow light, and the combination creates the perception of white light.
Oh, so it's like mixing colors but with light instead of paint. Clever.
Yeah.
So where do our terbium and europium oxalates fit into all of this? Could they be used in these WLEDs?
That's the really exciting part. Remember how we talked about terbium oxalate heptahydrate having that impressive quantum yield over 60% and that strong charge transfer band?
Yes, it was like the gold medalist of energy transfer.
Precisely. Those properties make it a very promising candidate for use in WLEDs, maybe even replacing those phosphors we talked about.
So instead of blue LED plus yellow phosphor, you could have a UV LED exciting the terbium oxalate, which then emits that bright green light. And maybe by tweaking the oxalate's composition, you could create different shades of white light.
Exactly. It opens up a whole world of possibilities for creating more efficient and customizable white light. And think about the benefits, not just brighter lighting, but even more energy savings, because LEDs are already super efficient.
Lower electricity bills, less strain on the environment. That's a win-win for everyone. It sounds like these oxalates could be a game changer for lighting technology. But I have a question. Are these materials easy to come by? Are we talking about something super rare and expensive?
That's a great question, and it's something scientists are definitely looking into. Rare earth elements, they're not as abundant as some other elements like iron or aluminum, but they are found in various parts of the world.
Okay.
And unlike some materials used in electronics, there are no major geopolitical concerns or supply chain issues associated with rare earth elements.
So not only are these oxalates promising for better lighting, but they come from readily available materials. That's fantastic. It sounds like we might be on the verge of a whole new era in lighting technology, and it's all thanks to these glowing crystals.
It's definitely a possibility, and this research is really just the tip of the iceberg. The more we learn about these energy transfer mechanisms, the more we can fine-tune these materials and discover even more applications.
It makes you wonder, what other amazing materials are out there just waiting to be discovered? It's like a whole universe of possibilities.
Absolutely. Who knows? Maybe someday we'll be walking down streets lit by glowing trees or living in homes that emit a calming glow, all thanks to this research.
It sounds like science fiction, but it's based on real science.
Hmm.
This has been an incredible deep dive into terbium and europium oxalate. It's amazing to think that something as familiar as light still holds so many mysteries. And uncovering these secrets could lead to some really amazing innovations.
Exactly, and it all comes back to the power of basic research. Sometimes the most groundbreaking discoveries come from simply asking questions and following your curiosity. You never know what amazing things you'll find.
That's a great point. So let's bring it back to our listeners for a moment. Why should they care about all of this? What's the big takeaway?
Well, this isn't just about pretty colors or cool lab experiments. It's about understanding the fundamental principles of light and energy, knowledge that could lead to more efficient and sustainable lighting solutions, and even brighter displays for our devices. Think about the potential impact not just for our daily lives, but for the environment too.
So it's about more than just lighting up our homes. It's about lighting the way to a brighter future, literally and figuratively.
Exactly. And I think it's also a reminder that science isn't just about facts and figures. It's about creativity, imagination, pushing the boundaries of what's possible. And who knows, maybe some of our listeners will be inspired to dive deeper into this world and make their own discoveries.
That's a great note to end on. But before we wrap up, any final thoughts for our listeners?
I think the most important takeaway is this: don't underestimate the power of curiosity. Sometimes the most ordinary questions lead to the most extraordinary discoveries. So keep asking questions, keep exploring. Who knows what you might find?
I love that. A perfect message to encourage everyone to keep learning and exploring. Well, thanks for joining us on this illuminating deep dive into the world of terbium and europium oxalates.
It's been a pleasure.
You know, it's amazing we started with just these two compounds, terbium oxalate and europium oxalate, and look where we've ended up. It really shows you how connected everything is, from the tiniest little atoms to, well, how we light up our world.
Yeah, it really highlights how interconnected science is, doesn't it? I mean, we've talked about
Yeah.
chemistry, a bit of physics, material science, even touched on the environmental implications.
Exactly. And the geopolitical side of things, too. It really shows that scientific breakthroughs, they don't happen in a vacuum.
Yeah, for sure.
It's like a giant puzzle, right?
Yeah.
And each piece, each bit of knowledge adds to the bigger picture, no matter how small. Even something like those water molecules we talked about, just shifting your focus to those tiny things
Yeah.
can completely change your understanding.
Absolutely. And it's often those unexpected insights, right? Those that lead to the most exciting innovations.
For sure.
And speaking of innovation, I think it's worth coming back to those WLEDs for a moment.
Yeah, good point.
We talked about how terbium oxalate heptahydrate, how it could make them even brighter and more efficient. But what does that actually look like in real life? How would you actually use it?
Yeah, that's a great question.
Yeah.
I mean, I'm imagining tiny crystals embedded inside those little LED bulbs, but I'm guessing it's probably a bit more complicated than that in reality.
You're right. It's definitely not just sprinkling crystals into a bulb. Huh.
Right.
Scientists are actually exploring a bunch of different approaches, like creating thin films or nanoparticles that can be integrated into the LED structure itself. It's a really active area of research, and the technology is evolving all the time.
So it's almost like scientists are becoming architects, designing the perfect little structure to harness the power of these materials. It must be a real challenge getting the chemistry right, but also making it practical.
Yeah, absolutely. And one of the big challenges is figuring out how to produce these materials on a larger scale, right? And making sure they stay efficient and stable. It's not enough to just make it work in a lab. You've got to be able to translate that to the real world.
That's so true. It makes you appreciate how much work goes into bringing a scientific discovery to life. From that initial, like, aha moment to an actual product you can use, it's a long journey.
It really is. But the potential rewards are huge. I mean, imagine a world where we could drastically cut down our energy use for lighting just by switching to these super efficient WLEDs. It could have a massive impact, from reducing carbon emissions to saving people money on their energy bills.
It really puts things in perspective, doesn't it? Even seemingly small advances in science, they can have a huge impact on our lives and the planet. Pretty inspiring. But I'm also curious about, beyond lighting. You mentioned other potential applications like bioimaging and solar energy. Can you tell us a bit more about that?
Yeah, definitely. These principles we've been talking about, the energy transfer principles, they apply to a lot of different fields.
I see.
So, for instance, in bioimaging, scientists are using luminescent materials to track molecules and cells inside the body.
Wow.
It lets them actually see biological processes happening in real time, almost like those materials are tiny little beacons illuminating what's going on inside ourselves.
That's incredible. So we've gone from lighting up our homes to lighting up the mysteries of life itself. That's amazing.
It is. And then in solar energy, researchers are looking at using luminescent materials to make solar cells even more efficient. So these materials, they can absorb sunlight and re-emit it at a different wavelength, one that's better for solar cells to absorb, potentially capturing even more energy from the sun.
Ah, so it's like they're fine-tuning the sunlight for those solar cells. Pretty neat.
Exactly. It could make solar energy even more viable, a more powerful, clean energy source.
It seems like the possibilities are really endless when you start exploring these materials.
They really are, and that's what makes this research so fascinating. It's not just about these specific findings, it's about what they unlock. New avenues to explore, new questions to ask. Science is all about that continuous journey of discovery.
And it's a journey that we can all be a part of, right? Whether we're scientists working in a lab or just people who are curious about the world around us.
Exactly. So, to everyone listening, don't be afraid to dive in, to ask questions, to challenge what you think you know. You never know what incredible discoveries you might stumble upon.
I love that.
Yeah.
A perfect message to wrap up this episode. Keep exploring, keep learning, and keep that curiosity alive. Thanks for joining us on this illuminating journey into the world of terbium and europium oxalate.
It's been my pleasure.